In Lesson 2.2, Basic Differentiation Rules, we'll abandon that wicked formula, that definition of derivative that we learned in the last lesson, in favor of some shortcuts. Now, don't take these shortcuts for granted. By the end of this chapter, you should be able to prove every one of the shortcuts you're going to learn in this lesson. Nevertheless, for the time being, you can certainly use these shortcuts as a way to avoid using that formula we learned in the last lesson. This will be much favorable, in fact. So in this lesson, we'll learn those shortcuts, we'll use those shortcuts, and we'll wrap it all up by finding the equations of tangent lines to given functions at given points. It won't be difficult, it just requires a little bit of algebra. So with that, why don't we go ahead and take a look at these shortcuts now. So we're going to run through these rules rather quickly. You'll find that a lot of them do make perfect sense when you think about it. So let's go ahead and begin by looking at the derivative of a constant function. Now remember back in lesson 1.1 we talked about the graphs of derivatives. And if we had a constant function, what was the rate of change at every point along that horizontal line? Of course, the rate of change would be 0. And so the derivative of any constant function is simply 0. The derivative of pi, for example, or the derivative of negative 5,000, it's going to be 0. With that, let's take a look at the power rule. The power rule is the one that you're going to use most often when you're finding the derivative of polynomials. This one is quite common. So all you need to do, we have x to the nth power. It's very easy. You simply drop the exponent down as a constant multiplier. And then we'll carry the same variable x, and we'll drop the exponent by 1. So x to the nth power simply becomes n times x to the next lower power. As a quick example, let's find the derivative of x to the negative third power. Of course, all we'll need to do here is just drop the exponent down. It becomes a constant multiplier. There's our x, and then we just drop the exponent by 1. So we get negative 3x to the negative fourth, which of course, if you wanted to, you could rewrite as negative 3 over x to the fourth. We'll take a look at a lot more examples, of course, but that's just a quick and simple one. So let's move down to the constant multiple rule. What happens if we have some function multiplied by a scalar multiplier? Well, it's very easy. That multiplier is just going to jump in front of the entire problem. So what we're actually going to get is c times the derivative of f to the x. No big deal. Then we just find the derivative of this function and multiply c back through our result. So nothing big there. Just as a point of information, as I said in lesson 1.1, we often write the derivative of a function as f prime of x. So we could write the constant multiple rule that way as well. So the sum and difference rules, no big deal. If we're doing the derivative of some function plus or minus some other function, all we really need to do is differentiate each function and keep whatever operation is going on between them. So no big deal, we just differentiate each function. So now we get down to the trigonometry rules. We kind of sort of proved this back in lesson 1.1 notes, but the derivative of sine x is simply going to be the cosine of x. The reverse is not necessarily true, though. The derivative of cosine is actually negative sine of x. If you want to prove that to yourself and see why that's the case, simply draw a graph of cosine of x and then find the derivative of each point along it, like what we did in lesson 1.1. So there are your general differentiation rules. Let's go ahead and see how we use these. We'll begin, of course, with example A. Probably the easiest general type function to differentiate is a basic polynomial, and that's what we have here, a quadratic function, 3x squared plus 2x minus 1. Now we can apply all the rules and take this step by step and go about it the long way, or we could do it quickly using common sense. Which way am I going to do first? Of course, the long way. So if we break this function up, and again we do want to differentiate this, so what I could do is I could differentiate each term separately. That would result in something like this. The derivative of 3x squared plus the derivative of 2x plus the derivative of 1. Or actually, that should be a negative 1. Let me explain real quick this d over dx notation. You can read about this yourself, do a little bit of research, but essentially all it's saying is we're doing the derivative with respect to x. Now, here in Calculus 1, where we're dealing with single variables, most of the time it will be a derivative with respect to x or theta or whatever. But when you advance in calculus and get into the multivariable fun and exciting stuff, you'll find that what variable you differentiate with respect to makes a big difference in what happens in your derivative. Anyway, just a point of information there. Let's go ahead and keep up this charade that we started. If we want to do the derivative of the quantity 3x squared, you'll notice that that 3 is actually a scalar multiple. So what I can do is move that 3 out front and simply do the derivative of x squared. That will use the power rule, of course. And we can do the same thing here. There's a scalar multiple of 2, which I can move in front, and I'll just do the derivative of x with respect to x. And here's the derivative of a constant. We know what happens there. We saw that with the constant rule. That's just gone. Alright, so good times there. If we want to go ahead and do the derivative of this thing here, the derivative of x squared, we just drop the 2 down, we have x, and then this will be to the first power. Over here, this will be 2 times the derivative of x with respect to x, which is really just 1. And so let's go ahead and finish this out. Looks like the derivative of our original function is simply going to be 6x plus 2. Alright, well, I said that there was a shorter way of doing it. What does that shorter way look like? Well, it's simply doing everything all at once. If we want to do the derivative with respect to x of 3x squared plus 2x minus 1, we can just take this term by term and say, well, the derivative of 3x squared, if I drop the 2 down, it'll turn this 3 into a 6. I have x. I don't really need the first power. It's not necessary. The derivative of 2x, well, the x will essentially go away. We're left with 2. And the derivative of negative 1 is nothing. So there's the short way of doing it. That's probably the way you're going to do it, and that will almost always be the way that I do it for real. I just wanted to show you how all of our rules can apply to one problem. So let's go ahead and take a look at example B, where we're actually going to have to rewrite certain terms in order to handle them quickly and efficiently. Let's take a look. I hope I've convinced you so far that differentiation is easy. Nothing too bad about it, but take a look at example B here. How would we handle something like this, where the exponent is in the numerator? Well, go back to that quick example that we did when we were talking about the basic rules. We noticed there that we had a negative exponent and we were able to handle it okay. So what we need to do here is rewrite this in a form where we can actually bring the variable to the top. And that would look something like this. Negative 1/2 x to the negative second. So I didn't really do anything special, although I did separate the constant scalar multiplier. So here's my scalar, and here's my variable expression. Well, now this shouldn't be too bad to do. If we want to do the derivative of negative 1/2 x to the negative second power, how are we going to do this? I'm not going to do it the long way. Don't worry, we'll handle this quickly. The negative 2 is simply going to jump to the front. And what are we going to get when we have negative 1/2 times negative 2? Well, of course, those are essentially just going to cancel out, become 1. And so we have our x, and what are we going to do to the exponent? That's right, we're simply going to subtract 1. So what we end up with is just x to the negative third power. Now, some of you are going to want to turn that into 1 over x cubed. You're certainly allowed to do it. There's no problem with that. But later on in the year, you're going to find that doing things like that actually complicates problems. My advice to you, leave it with negative exponents. It's not that big of a deal. I know you learned in Algebra 2 that that's a horrible, terrible thing and the world will explode. But negative exponents in calculus are perfectly acceptable. So, with that, let's take a look at example C that has a real nasty term in it, 4 to the 12th power. Let's see what we do with that. So here in example C, like I said, we have a nasty 4 to the 12th power. Go ahead and try differentiating example C real quick before we do it together. we want to catch you. If you are making mistakes, now is a great time to catch that mistake. So give it a quick shot. I'll wait. Okay, hopefully you've tried it now, or at least paused and fast forwarded this video. How many of you tried differentiating 4 to the 12th as 12 times 4 to the 11th? If you tried doing that, bad news. That is absolutely incorrect. 4 to the 12th power is in fact a constant. And so if we wanted to differentiate 4 to the 12th, that's just going to give us 0. 4 to the 12th looks like a polynomial, but it's really just a constant. 4 times itself, 12 times, has no variables in it at all. So when we differentiate that part, it's gone. Now, how do we differentiate the square root of x? That might be a different story. There's certainly a variable there. How do we do this? Well, just like in example B, we need to rewrite this problem. And the way we're going to rewrite it is by calling square root of x, x to the 1/2. Now this is a very easy situation to deal with. Just using the power rule, we see that this is just going to be 1/2 times x to the negative 1/2. And there we go. There's our answer. Again, some of you are going to decide that you want to write it like this, and you're certainly welcome to do that. It is correct. There's nothing wrong with it. But my advice, stick with the easy answer. It's usually the best. All right, well, if you take a look at example D before we get there, you'll see that it's ugly. Let's talk about simplifying exponents. You've done it before, and we'll do it again. Back in Algebra 2, many of your classmates struggled extensively with the properties of exponents. Hopefully, you were not one of those people, because in this problem right here, we are going to have to simplify this function before we differentiate it. So if we take this term by term, in other words, if we just put x squared under each one of these terms, then all we really need to do is subtract the exponents in each case, and that will simplify it. So f of x could be rewritten as, let's see here, this would be 2x to the 3/2. This would be minus x to the 1/2. And this last one would be plus 5x to the negative 3/2. Now that we've rewritten it in a more polynomial-ish form, we can go ahead and find the derivative of it. This shouldn't be too difficult, even though we're dealing with fractions. That shouldn't bother you too much. If we drop the 3/2 down to the 2, that will turn into a 3x. Subtract 1 from the exponent, we'll have 1/2. For the second term, we can drop the 1/2 down. X, if we subtract 1 from this, we'll get to the negative 1/2. And finally, here, 5 times negative 3/2. That's kind of ugly, but no big deal. It'll be minus 15/2 x to the negative 5/2. Now, at this stage, do you really want to simplify these negative exponents by bringing them down to the denominator? You could, but it would be pretty nasty, and there's really no reason to go about doing it. I'm not even going to write it here. So here is our derivative. No big deal. Just know that sometimes you need to rewrite a function, sometimes you need to simplify a function, but then you can differentiate it, and it shouldn't be too bad. Well, let's move on to the examples E and F, where we're going to make use of those trigonometric rules, the sine and cosine, and see how those look in action. In example E, we're dealing with the function that you see here, x minus cosine of x. Now, we can separate these using the sum and difference rules, and if we want to find the derivative of this, what we can do is find the derivative of x, and then subtract the derivative of cosine of x. Maybe you could do this in your head. I'm just writing it out for brevity's sake. So the derivative of x, as we've already discussed, is simply just 1. And the derivative of cosine, if you look back at your trigonometric rules, is actually negative sine of x. And so our final derivative of this function is actually going to be 1 plus sine of x. One big thing that students often get caught up on is the sign to use when you're dealing with sine and cosine, the SIGN sign, positive, negative. Don't get lost with all of this. The derivative of sine is just cosine. But the derivative of cosine, as we've done here, is negative sine. Commit that to memory. Don't forget that. That is always one of the sticking points. If there's a multiple choice question, I guarantee two of the answers will differ by nothing more than that negative sign. They're trying to catch you. They're always trying to catch you. So watch out for that. So now we'll go ahead and take a look at example F, where we have a sine and a cosine to deal with. It won't be a big deal. You'll see. And as promised, here is your function with both the sine and the cosine. Just to let you know, we'll be learning about all the other trig functions later, the tangent, the cotangent, cosecant, secant, all those. We'll be learning them later, but we want to start easy. Sine and cosine is good enough for now. So let's go ahead and differentiate this function. Don't put an x in there. Understand this is now a function of theta. You see the thetas. There's no x's in this problem. So what is the derivative of sine? Of course, that is just cosine. And here we have 2 cosine theta. What are we going to do here? Well, the derivative of cosine theta is negative sine. And so the second term will turn into negative 2 sine theta. And the derivative of negative 1, of course, is just 0, so I'm not even going to write that down. So there's our derivative. No big deal. That was an easy example. And now what we're going to do is take a look at g and h, in which we're going to find the derivative of the function in order to find the slope of the tangent line to that function at a given point. And then we'll use a point slope formula. It'll be easy. We'll just do a couple examples and then we'll be on our way. So in example G, we're asked to find the equation of the tangent line to the graph of the function at the given point. So I've went ahead and graphed it for you there. You can see what this polynomial looks like, x cubed minus 5x. Nothing surprising there. And I've gone ahead and marked in blue the point that we want to find the tangent line at. So let me just show you what this tangent line would look like. There it is. And so we want to find the equation of that tangent line. Now certainly one way we could do it is to actually draw it and then look at the slope and the y-intercept and all that good stuff. But what if it was a function that we couldn't graph or whatever, something along those lines? What we would need to do is find the slope of the tangent line, which is actually the same as the rate of change of this function at that given point. How do we find the rate of change? Well, the rate of change is just the derivative. So if we find the derivative of this function, of course, that would just be 3x squared minus 5. That's the rate of change at any point on the graph of this function. Let's find the rate of change at this exact point, at 1 comma negative 4. To do that, we just plug 1 into x for the derivative, and we can see that that would just give us 3 minus 5, negative 2. So there is the slope of our tangent line. Now that we know that, we have the slope, we can say that the slope is negative 2. We have a point, which is 1 comma negative 4, and we can use that information and the point slope formula to find the equation of the tangent line. You remember the point slope formula, right? That's the one that says y minus y sub 1 equals m times the quantity x minus x sub 1. If you have forgotten that, remember it now. Write it down, paste it up on your mirror so you see it every morning and evening. Whatever you need to do, remember that point slope equation, because that right there is going to give us our final answer. Y minus negative 4 equals negative 2 times the quantity x minus 1. And there we go, there's your final answer. Now if you want to simplify it, fine. We can say y plus 4 equals negative 2 quantity x minus 1. If you want to do that, that's fine. If you want to distribute the negative 2, that's fine. If you want to turn it into a slope-intercept equation, you can. But I'm going to caution you. If in the process of going from the point-slope equation to the slope-intercept form, if you do make a mistake in that process, you will be penalized. So really, honestly, it's best just to leave it right here. Don't simplify it. Don't mess around with it. Just leave it that way. It's good enough. And so with that, let's take a look at our final example where we're basically doing the exact same thing again. For our last example, I'm not going to show you the graph of this function right off the bat. Let's go ahead and find the equation of the tangent line to the function at the point 2 pi comma 2 pi. And afterwards, I'll show you the graph with its tangent line, and we'll see if you would have been able to figure that out on your own. So the first step, we already have the point that we're using, so we really just need to find the slope of the tangent line. And as we talked about in the last example, the slope is really just the derivative, which in this case is 1 plus cosine x. Alright, great. If we go ahead and plug that x value in so that we can find the derivative where x equals 2 pi, you'll see that we have 1 plus the cosine of 2 pi. And now we need to think back to pre-calculus and use a little bit of our unit circle knowledge, or if you just memorize it, or whatever the case. Cosine of 2 pi, well, the cosine of 2 pi, that's just 1. And so it looks like the slope of our tangent line is going to be 2. Well, we have our slope, we have our point, so if we put this all together, we'll have y minus 2 pi equals 2 times the quantity x minus 2 pi. And that is the correct answer. That is what we get. Now, if you wanted to be adventurous and turn that into a slope-intercept form, I'll tell you that what you would get would be y equals 2x minus 2 pi. Once I show you the graph of this, we'll see if you would have been able to figure out either that slope or that y-intercept. Let's take a look at it now. Sure enough, there's the function with the point marked, and there is the tangent line. Well, looking down at the y-intercept, yeah, it's a little bit less than 6, but would you have known it was actually negative 2 pi? And furthermore, you could have tried to reason out what the slope is, try to make some stair steps and count them, but would you have figured out that the slope was exactly 2? Maybe you could have figured out the slope, but that y-intercept, it's really just best to use calculus to do this. And now that we've gone through lesson 2.2, we've found some basic differentiation rules, a lot of them being very common sense. We applied some of those rules to a few different examples and saw how it all worked out. Sometimes you need to simplify a function, sometimes you need to straight rewrite a function before you can differentiate, but then it's really no big deal. From there, we found the equation of tangent lines to functions at given points, remembering that all we really needed to make the equation of a line is a point and a slope. So remember all this as you proceed through to your homework, and good luck.